have this opportunity to give a speech about the neighborhood optimization method for shipping body plot with larger face margin. So you can see the author list here. It is composed with two authors from the Northeastern University in China, and the other one is from the University of California, Merced. Those are the contents I'm going to talk about for this speech. The first question is why we want to use fractional order controllers. Let's see this figure. The x-axis is the power of integrator, and the y-axis is power of derivative. We can imagine that this point stands for the proportional and derivative controller. If the power of derivative is 1, and for this point it stands for proportional integrator controller, and for this one, the power of derivative and the power of integrator are 1. Then we have a proportional integrator, integral, and derivative controller. So this is the integral order PID controller. So how about the other areas? So we can know that it is a fractional order PID controller. So from this figure, we got to know that fractional order controllers provide us a more accurate way to describe a control system. Therefore, intuitively, the fractional order controllers should be better than integral order controllers. The next question is how to tune those fractional order controllers. There are some existing tuning methods. The first one is based on equations. We build equations to make the face flat at crossover frequency. So this is the first method. Also, there are some methods based on optimization method. And the following four are how to build the constraints. Some of them had sensitivity constraints. So what's the benefit of this neighborhood face margin method? And there are 3 benefits. The first one, classic flat face method cannot guarantee there's a solution existing. When we use the flat face method, sometimes we plot two plots and they do not have cross points, so we cannot get a solution. At that time, we should try again to change to another parameters. But the NPM method doesn't have this issue. The second one, NPM method doesn't have local minimum issues because face function is continuous. Some of the optimization-based methods have used index such as ITAE. However, those indices are not continuous. That means they have local minimum issues. If the optimization function goes to the local minimum, the result is not going to be the global optimum method. And let's see the last one. Comprehensive sensitivity analysis has been done for NPM method. However, this sensitivity analysis is not in this paper. It is in an extended version of this paper. We have submitted this sensitivity analysis to a journal. However, I can tell you that the sensitivity analysis proved that this method is not sensitive to its parameters. So it gives us an easier way to design the FO controllers. So let's see, what is NPM method? It stands for Neighborhood Phase Margin Method. Let's see this figure. It is the phase plot in a body plot. And omega c is the crossover frequency. If you want the control system to be more robust, we want the phase do not change much around the crossover frequency. So we have got two control points. The first one is omega c minus, and the second one is omega c plus. We suppose that if we get the phase at omega c minus and the phase at omega c plus to be as close as the phase at the crossover frequency, the control system would be very robust. So this is our main idea of the NPM method. Based on this, we have established the optimization problem. So let's go to the problem formulation part. This is the objective function. First, we have the phi mr. The phi mr stands for the desired phase margin, and the phi m is a phase margin. Phi m minus is a phase margin at omega c minus, and phi m plus is the phase margin at omega c minus. And the absolute function gets the distance between the phase we want and the actual phase. The last two parts tries to get the phase to be as large as possible. The number m, the parameter m, is the weight to balance those two parts. Based on this, we have built a FOPD controller tuner. It is a MATLAB app. Let's see a small video that tells us how to use this small app. We have the web address. This is a link to tell us how to get the source code for this FOPD tuner. After we got this main.ml app file, we can right click and select run to open it. And then we can click tune IOPID controller to get the tuned to the tuned IO-PID controller. After that, click the tune FOPD controller. We can get the body plot and we see the face is flat. FOPD is faster and it has less overshoot. This is a robust analysis. So that's all for the video. Let's see the results. The body plot is very flat at the crossover frequency. However, it is not as flat as the one from flat face method because it has a slope. The slope is not zero. Also, we have built a Simulink model to evaluate step response performance. The upper one is a fractional order controller, and the lower one is an integral order controller. We have set those parameters like KD, KP, IOKP, IOKI, ILKD, and those K and tau in the plants in MATLAB scripts in the previous MATLAB app. So after we run this model, we can get the output from the fractional order controller and the integral order controller. This is a comparison between those two step responses. Again, we can see the overshoot is less and the rising is faster for FOPD controller. This is the control signal. The FOPD is much faster. The robustness analysis. When the plant gain changes to half and 1.5 times, the FOPD controller maintains a good performance. That means the overshoot is not very much. However, the integral order controller has larger overshoot sometimes. The next part is the sensitivity analysis. We try to change the initial value of lambda. The lambda is the power of the fractional order. It has a range between -2 to 2. Even though we change the initial value, we can get the best fractional value almost the same. After that, we have put the design controller into a nonlinear benchmarking system. We have identified the plant model in SimScape. It is a drone model. After that, we designed the controllers using our MATLAB app. And then we use the simulation environment to get the step responses. From this figure, we can see the fractional order controller works faster and has less overshoot. Also, we have done the robustness analysis for the two controllers. We can see the purple one has more overshoot. Above all, we have got all the conclusions. The neighborhood phase margin method is proposed for tuning fractional order PD controllers. A comprehensive sensitivity analysis has been done for the proposed method. Nonlinear benchmarking environment has been employed to evaluate the proposed method. Thank you for watching. So it's time for questions. There are the references. So it's a question time. Thank you.